Hi, welcome to this talk on a randomness-efficient massively parallel algorithm for connectivity. My name is Anna, and I'm a PhD student at Stanford. This is joint work with Moses Charikar and Liang Tan, both at Stanford. In this talk, we will focus on the massively parallel computation model, or MPC. In MPC, the input is distributed to a collection of machines, and the computation proceeds in synchronous rounds. In each round, a machine receives some messages from the previous round, performs some local computation on those messages, and then sends the results to other machines as input for the next round. The main complexity measure in MPC is the number of rounds it takes to finish the computation. In this talk, we'll work in the strongly sublinear MPC regime, which means that if n is the input size, then each machine has local space at most O of n to the epsilon for some constant epsilon smaller than 1. This limits the total size of the messages a machine can send or receive in a single round. We will consider the problem of graph connectivity in MPC, where given as input an undirected graph on n vertices and m edges, the goal is to decide whether the graph is connected. It is well known that connectivity can be solved in O of log n MPC rounds. In fact, we know that this can also be achieved in the more classical PRAM model, and there are efficient simulations of PRAM algorithms by MPC. And recently, for MPC, Liu and Tarjan gave an O of log n round algorithm that is simpler than the non-PRAM algorithms, and their algorithm takes optimal O of m total space. On the other hand, if we allow the graphs to be parameterized by the diameter d, then it turns out that connectivity can be solved more efficiently for small diameter graphs. Recent breakthrough of Andoni et al. Give an MPC algorithm that takes O of log d log n rounds. And this is further improved by Behnezad et al. To O of log d plus log n rounds. And just like the algorithm of Liu and Tarjan, these two algorithms both take optimal O of m total space. As compared to the previous works, which focus on improving the round complexity, in this work, we take a different perspective by mainly focusing on the randomness efficiency. In particular, our goal is to reduce the randomness usage of MPC algorithms. Besides being interesting from a theoretical point of view, designing randomness-efficient algorithms is also desirable in practice because it can be hard to obtain high-quality random bits. Now let's revisit the connectivity algorithms that we mentioned on the previous slide, but now from the perspective of their randomness complexity. First, this O of log n round algorithm of Liu and Tarjan is a deterministic one. On the other hand, the round efficient algorithms of Andoni et al. And Behnezad et al. Are randomized and both use omega of n random bits. The main contribution of our work is a new MPC algorithm for connectivity that achieves a super polynomial saving in the randomness complexity as compared to the two randomized algorithms above. Moreover, our algorithm has an efficient round complexity that is parameterized by d. So now let me talk more about our randomness-efficient connectivity algorithm more formally. We show that for graphs with diameter d equals 2 to the little o of log n over log n, connectivity can be computed by a strongly sublinear randomized MPC algorithm with R equals O of log d plus log n rounds, O of m machines, and log n to the O of R random bits in total. Here, in terms of the range of d for which our algorithm is applicable, we can think of d as being roughly polylog n or even larger, but not as large as n to the delta for some constant delta. Our algorithm has the same round complexity as that of Behnezad et al., although we use more machines. And finally, the randomness complexity of our algorithm is little o of n to the delta for any arbitrarily small constant delta, which achieves a super polynomial saving. So how do we construct this algorithm? It actually follows from a general framework that we developed for converting randomized PRAM algorithms to randomness-efficient MPC algorithms. Before we go into the details of our framework, let me first recall the PRAM model and what we know about connectivity in PRAM. In PRAM, the computation is carried out by a collection of processors in synchronous time steps, and the processors have access to a shared memory. In each time step, a processor can read from or write to a cell in the shared memory or do some local computations. And it is well known that PRAM algorithms can be efficiently simulated in MPC. As we mentioned earlier, connectivity has been extensively studied in PRAM as well. There are several PRAM algorithms in the literature that solve this problem in O of log n time. For example, the algorithm of Heparin and Zwick achieves this using an optimal O of m over log n processors in the Wiki's version of EREW PRAM, where each cell can be read or written by at most one processor at a time. And very recently, for graphs parameterized by the diameter d, Liu et al. Provide an efficient O of log d plus log n time algorithm using O of m processors in the strongest version of CRCW PRAM, where multiple processors can attempt to read from or write to a cell concurrently. Now let me state our general framework that converts randomized PRAM algorithms to highly randomness-efficient MPC algorithms. Suppose a function f on n input bits can be computed by a randomized PRAM that uses at most a polynomial number of processors and memory cells, and runs in little o of log n over log n time steps, where each processor can generate a polylogarithmic number of random bits in each time step. Then we show that f can be computed by a strongly sublinear MPC algorithm that preserves the number of machines and the run complexity while only using a total of log n to the O of r random bits. Our framework applies to all versions of PRAM algorithms, in particular the strongest CRCW PRAMs. And now, to get our MPC algorithm for connectivity, we simply apply this framework to the CRCW PRAM algorithm of Liu et al. Our algorithm preserves the O of log d plus log n round complexity and also uses O of m machines. And finally, let me say a few words about the main ingredients that go into our framework. At a high level, our framework extends the classical de-randomization techniques for small depth Boolean circuits, which is a weaker computation model, to CRCW PRAMs. The key ingredient here is the construction of a pseudo-random generator that can fool CRCW PRAMs. And we show that the classical Nissan-Wigderson generator does this job. And just as in the circuit case, the construction of this pseudo-random generator relies on the existence of an average case hard function. We show that the parity function, which is known to be average hard for circuits by classical results, is also average case hard for the stronger model of CRCW PRAM. Thank you.